Okay, class, this is your first learning assignment in the online video format. I want you to notice that what we're going to do is talk a little bit about what we're going to do. We're basically doing chapter 16 and 17 in series circuits, sections 1, 2, and 3. Try to avoid following the formulas that are in the book. Keep looking at the way that I'm doing things, and our way will be repetitive over and over and over to the point where you will master this in no time. We're going to be computing voltages, currents, and resistances, not power, in these AC circuits, okay? And let me change the thickness of my marker here, or we won't be able to see it. What we start off with is a typical, in this case, 4-component resistor capacitor circuit. I want you to take a look at the circuit in blue right here, and you'll see there are 4 parts. It doesn't really matter what the order of the parts are. It could be capacitor, capacitor, resistor, resistor. It could be capacitor, resistor, capacitor, resistor. This is a series circuit. It doesn't matter what the component locations are going to be. The battery will supply the same amount of current regardless of location. And being closer to the battery will not mean that your voltage will be bigger. If you remember in chapter 5, series circuits, the largest resistance gets the most voltage. Well, we've graduated to impedance. If you look at the diagram on the right in red right here, you'll see that we've redrawn the circuit and we've replaced the components with boxes. I recommend you follow the same protocol to keep things straight. You are now in circuit 2 looking to lay down the foundation for solving that circuit exactly how you did it in chapter 5. So, the main obstacle is the 2 capacitors. They are not in ohms. They are in microfarads. And so, as you can see down here in the green in step 1, all the caps and inductors must first be converted to ohms. When? Always. So our first step down here in blue is to find x sub c1 and x sub c2. Now, this particular problem, they're exactly the same, so there's no need to do the calculation twice. And what you'll see is that I plug in, and what I recommend you do is, I'm working these problems with the answers already inserted. If we didn't do that, these videos would take 4 hours to construct and listen to. So I'm shortening the curve. I'm hopeful that you will go back and make these calculations or pause the video and prove to yourself that you are capable of calculating the reactance, the capacitive reactance of capacitor 1 and 2. If you look at the answer over here, this is what you're striving to get. And you'll notice that 1 over 2 pi times 10k times 0.01 microfarad will give you the 1592.3 ohms that you seek. But since it's a capacitor, every capacitor gets slapped in the rear with an angle of -90. Not some capacitors, all capacitors. So now we truly have circuit 2, which is located up here in the red area, circuit 2. We have it all in ohms. Notice that I've replaced all the resistances with impedances. I've made them boxes. They're all going to be treated 100% exactly the same way, except resistors will have a 0-degree phase angle. Take a look at circuit 2 and see that my 1,000 ohm resistors have 0-degree ohms, and my 2 capacitors are identical at 1592.35 with a phase of minus 90. Now, it doesn't matter if you're doing series or parallel. Step one is always find the total resistance. Now, since we are dealing with capacitors in addition to resistors, this becomes impedance. So we've got to use our polar and rectangular capacity of our calculators. And if you notice down here in the black check mark, ZT is basically the sum of the four impedances. We treat them all the same. R1, C1, C2, R2, they're the same. But we distinguish them by putting 0 degrees on the back end of the resistance values and minus 90 across the capacitors. When we get to inductors in the next problem on this paper, you are going to use positive 90 instead of negative 90. So take a look at that calculation of ZT. You're going to have to try to come up with that answer on your calculator on your own. You're going to run into problems. Look at my equation for ZT circled in blue down here. You'll see that my resistors have brackets around them. My capacitors have brackets around them. Every component has brackets. If you fail to do that, your calculator will reject your computation with an error message. If you're not able to get the answer that I got, perhaps your calculator is in rectangular mode instead of polar mode. Perhaps your calculator is not in degrees mode. You'll have to go to the mode function of your calculator to make sure that you have turned on degrees mode. And also, you have to make sure that your calculator, way down at the bottom of the mode key, there is an option to compute approximate values. And that's what you want. You want an approximate value. Page 2, step 2. Now it's time to find the total current. Since we have the total voltage and we have the total current impedance, then we can set this equation up here, just Ohm's law, and come up with the answer in front of the check mark. Go ahead and try that on your calculator. Pause the video. See if you can mimic what I've done. Once you've done that, and you've gotten through all the bugs in your calculator, you'll notice that because it's a series circuit, all the currents are the same. And you'll also notice that the currents are all computed basically using Ohm's law over and over and over. The only thing that changes is not the current, but actual resistive component. Is it a resistor? Is it a reactance from a capacitor? And as you can see, I've computed it 4 times. Every time I compute with a resistor, I multiply by 1,000 ohms at 0 degrees. And every time I've computed the calculator, down here where the blue arrow is, when I've calculated the capacitance, I've taken the current at 57.87 milliamps and snuck in X sub C and 1 and X sub C2, both at negative 90 degrees. If you have any trouble, shoot me a message, but you should be able to reproduce step 3. And then when you're done, you should be able to check using Kirchoff's voltage law that the sum of the voltages shown here, Kirchoff said, if I have a battery and I have 1, 2, 3, 4 parts, those 4 parts will steal every volt of that battery. You cannot conserve the voltage. So if you look at the voltages that we just computed above and we add them, we end up with 10 volts at 0 degrees for a battery is equal to 10 volts, 0.0040 at an angle of 0.0132. That's roughly what your exact check answer is going to look like. It'll be close to 10. It might be a little high, it might be a little low, but just a little. And the phase angle will be a decimal zero something. That's what an accurate computation looks like. Now, I want to say one more thing about the battery. You'll notice here in yellow down at the bottom here that the battery shows up as a 10 volt peak to peak signal in the problem, and we always give the battery a 0 degrees reference value. That's what you're going to use in all your computations. Sometimes it'll be 5 volts at 0 degrees, sometimes it'll be 10 volts at 0 degrees, etc., etc. Now, that ends your RC series circuit. You'll notice that in this circuit here, I'm not going to sit here and walk you through it like I did the other problem. I'm just going to suggest that this circuit is the same method that was used for RC circuits on the first couple of pages to compute the voltages, the currents, and the impedances. You should be able to stack this problem, take a picture of this problem, write this problem down, and walk your way through just like we did the RC circuit problem. You'll see again that the battery is 10 volts peak to peak at 0. The frequency of 10,000 hertz has produced 2 new values for the inductors, and the resistors are unaffected by frequency. So we have a 10 millihenry and a 10 millihenry inductor, which is going to produce, the same voltage across both parts. I'll let you follow the calculation of impedance right here, ZT. Notice that it's the same equation we used with the capacitors. It's the same equation we used in series circuits with the resistors. The symbol was an R, but it was the same equation. And I want you to check your answers to be sure that you're getting the polar and the rectangular answers, or that you can switch between them, because that is pretty important. Okay, let's see what's on this page here. Here's the rest of the computations. You'll find that they go through the same exact well-documented sequence that the RC circuit went through in pages 1 and 2. And I'd like you to proof these calculations out and get to your homework. Okay? Notice how close the 10 at 0 is equal to 9.983 at negative 0.05. A very well computed problem. Good luck with your homework.